a moment to breathe and relax.
Beautiful. Thank you for joining me in this session. Don't forget to breathe and happy stretching.
Today tastes like a Sunday barbecue. And it never tasted this good.
Okay, grade 12s. The next chapter or part that we have to have a look at is chapter 19, Oscillations. Now, before we started with the lesson, we had a look at a couple of videos, all right, and we saw certain things, and I will refer back to those videos as we go on. So, they say there, oscillation, and oscillation is simply a regular, repetitive, to and fro motion. All right? Now, somebody's sitting on a swing, and you push them along. That's also an oscillation. All right? If I took let's say it's a swing, or it's a pendulum, it can also do the same thing. If I lift it up, and I let it go, this pendulum, or oscillating system, is going to oscillate at a specific frequency. Because if I just give it a single displacement and it starts vibrating, we say this thing is vibrating at one of its natural frequencies. Now, if you're in a swing and they lift up the swing and you start swinging backwards and forwards, eventually what's going to happen? It's going to run down, you're going to stop. If I wanted you to keep on going, I would have to push. But with a specific rhythm, okay? If the frequency with which I push that swing is the same frequency as the vibrating system, we are going to eventually get the amplitude of the vibration to increase. And that is what we saw with the Tacoma Narrows Bridge video. What happens is, if I have a vibrating system and I force a vibration, but it has the same frequency as that object that is vibrating, we find that the amplitude of the vibration will increase, and if we keep doing it, it will keep on increasing. And that is why the bridge eventually broke. Initially it started vibrating at one of its natural frequencies, but on that specific day, the speed of the wind caused a vibration that had the same frequency as one of the natural vibrations of that bridge. And it caused the amplitude, because you see the bridge doing this, it caused the amplitude of the vibration to increase. When we looked at the video clip on the Barton pendulum, we saw that, let's just take another page, we had a string there, stand there, and we had little weights hanging from the string, and then we had one heavier object. And all of them were standing still, and they displaced this one, and it started swinging backwards and forwards. The vibration is transferred through the string, and all these other little weights started swinging backwards and forwards at their own natural frequency. One of the weights started increasing the amplitude of its swing, because the frequency of the forcing, the one forcing the vibration, was the same as the frequency as one of the weights. And that one will start swinging with an ever increasing amplitude. We call this resonance. When do we get resonance? When we have a forcing frequency equal to the natural frequency of the object. We find that the amplitude of the vibration will increase. When I was a child, young, where we lived was there near, it was in Cape Town, but it was near to the, not near to the airport, but the aeroplanes that would come into land flew directly over our houses. And it was in the time of the Concorde. Now the Concorde is a much faster aeroplane than the others. And he has to come in fairly low because they're coming into land. When the Concorde comes in, they say to us, open your house windows. Because the supersonic jet is going to cause a vibrational frequency that if you do not somehow cancel that vibration, it's going to vibrate more and more and more, and it's going to shatter the glass. When there's an earthquake, I don't know if you've ever seen the pictures after the devastation, you see heaps of bricks and rubble as the houses collapsed, and then sometimes there's this one little lonesome building standing upright as if nothing had happened. Have you ever seen a picture like that? Yes. Why did the one building not collapse, but the others did? No. When there was an earthquake, the earth is vibrating. All right? When that vibration reaches the natural frequency of the building is going to vibrate with an ever increasing amplitude. Which are the ones that shattered and fell down? Those buildings, not necessarily the tallest, but those buildings where resonance started occurring. The one that remained standing, what happened? Was there any resonance? Probably not. Or if there was some other system that could cancel it. When they build buildings in Japan, lots of earthquakes there, they build them earthquake safe. How do they do it? They build into the structure, the engineering structure, they build in a damping system. And it's as simple as, for example, now the engineering itself is not all that simple, but for example, if I had a tall building, all right, and in the top, I put a tank full of water. If the building sways in that direction, what does the water do? It tends to stand still, but when the building comes back, the water moves in the opposite direction. So it cancels the vibration of the building. They can do similar ones, something similar to that can be done if you hang a heavy weight. If the building shakes to the one, the weight comes after a while, and then it shakes back, and the weight cancels the movement. It's damping the motion. Well, it depends. They don't normally do that at this point. Or, into the foundation, they build a system that if the earth shakes in that direction, the building goes in that direction, and when the earth comes back, they do that. It cancels the vibration. We say damping occurs. If I looked at it in terms of waves, well, if this was the vibration, the damping cycle has to be 1/2 wavelength out of phase. And it will cancel the vibration. You follow? Okay, so let's check in your books. They start off, they're on page 341. This is higher level only, oscillations. They say periodic movement in which a pattern of movement is repeated over regular periods of time is very common all around us. Then they say the pendulum is a simple oscillator. If you start a pendulum oscillating, in other words swinging, it will continue oscillating forever unless it is damped. Now it makes me think of these perpetual motion toys that you get. Very little friction on it, so you lift the little ball up, it will swing backwards and forwards forever. Alright? Unless there was some friction that could damp the movement, which eventually does happen. Alright. Every pendulum will oscillate at its own natural frequency. Just have a look at this thing. My pendulum, if the string is this long, that so many cycles per second would be the frequency of this oscillator, the natural frequency. If I shorten the string, can you see that the frequency is higher? Okay. So every single object, and it's, well, if it's a pendulum, it's got to do with the length of the pendulum that will determine the natural frequency. But buildings, because they are much more complex, have usually got more than one natural frequency at which it can vibrate and then start resonating. So when they talk about a natural frequency, it's just very simply the frequency at which something vibrates after one. If I take my page and I displace it, well, that's the frequency. Why does this one not keep swinging there and there and there and there? Yes, I've got lots of surface area along and there's some air friction. All right, that's why this one is damped after 1/2 cycle. Okay. Yeah? Yes, then it should keep going. All right, because there's no friction. Unless the elasticity of the material over here where it goes backwards and forwards. But if I could attach it in such a way that there wasn't friction there, it should keep swinging. Okay. They say you have studied the movement of a pendulum and you have found that the frequency of a pendulum depends only on its length. It does not depend on the mass, and it does not depend on the size of the initial displacement. In other words, here I have my string, I've got a mass piece on the bottom. That's the frequency of the vibration. If I would remove this mass piece and add a smaller mass piece to it, a lighter one, is it going to affect the frequency of the vibration? No. Okay. Whether I displace the weight to there and let it go, or whether I displace the weight to there or let it go, does it affect the period? Nope. The only factor that affects the frequency or period of this oscillator is the length of it. All right? If it has a length of 1 meter, the period will be 2 seconds to go from there to there and back to there. It will be 2 seconds. Okay. Then on the next page, they try and explain that the vibration of the oscillator can be sort of translated into a graph that looks like that. Okay? If I have an oscillator, let's say I have a bucket and I've got a hole in it and I fill the bucket with sand and I set it swinging like this and I pull a sheet of paper underneath it, the pattern that will be formed on the paper will look like that. All right? Because from there is the 0 position to a maximum, there, back to 0, there, to a maximum in the opposite direction, Daar. All right. Back to 0. There. Maximum in the opposite direction. There we go. Do you understand? So we can translate a vibration into a sine curve. And from that we can determine wavelength and period and frequency. All right. You must what? I don't know about that one. But okay, let's carry on then. Now they say, from the table, you can see that the velocity in simple harmonic motion is varying in the same way as the displacement. Listen. Here's my pendulum. This is very important. This is high-level work. If I look at this pendulum, let's say it starts moving over there. What is the speed over here? 0. The speed over here? Maximum. The speed over there? 0. Over here? Maximum. Over there? Okay, so if I... Seriously? All right. The red graph is my pendulum swinging. All right? And I want to start it over here. Let's just start it on the 0 position. Okay? No, I need to start it on the maximum. Okay. All right? So my pendulum is displaced. Maximum displacement. What do we know about velocity? Okay, so here we have displacement. Here I have velocity. So when it's at maximum displacement, what is my velocity? 0. There we go. All right? Now, it's going to go faster, faster, faster. Maximum velocity, ne? All right? So, well, if this is the displacement over there, here we have 0 displacement, but at that point, we will have maximum velocity. All right? So now it goes up on the other side. What happens to the velocity? 0, but the displacement is maximum. So there. All right. Can you see? Yes, I think it's actually going to go in the opposite direction. My graph should actually look like this. Let's do it there and there. Okay. Over here, we have 0. Over there, I should have maximum. Over there. Over here, I should have 0. No? Okay, so we will get the graph to look like that. No, I was right the first time around. No. Yeah. What is this distance? No. No. It's half a wavelength. It's not half a wavelength, it is quarter of a wavelength. Okay, so when the displacement is maximum, the velocity is 0. When the displacement is 0, the velocity is maximum. Now listen to, if I read the sentence that they say. They say, from the table you can see the velocity in simple harmonic motion is varying. All right, from, well, maximum 0 velocity, maximum 0, maximum. They say in this, it's varying in the same way as the displacement, but it is 1/4 of a cycle behind. All right? And we say that the displacement and the velocity are out of phase with each other. They are out of phase by 1/4 wave cycle. Now, I want to show you something. I actually want to clone this thing. Okay, here we go. There. The wave cycle is 1/4 wavelength. Ay, kom hier. 1/4 wavelength out of phase. You see that? That is what the graph should look like. So I should actually, yes, it is right. All right. So it will go there, and there, and there, and there. You follow? Sien jy dit? All right. Now, if we go and have a look at the acceleration of the pendulum, all right, gravity makes it accelerate. The acceleration, yes, is going to go. Positive acceleration, it's going to go faster, 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 fastest. And now, negative acceleration, slower, 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 slower. Then, positive acceleration, faster, 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 faster. Negative acceleration, slower, slower, slower. So, what happens is, when you go and look at the curve, then we find that the acceleration also has a sine curve shape. But when we draw the acceleration, we need to draw it 1/4 wavelength. There it would be on it. So 1/4 wavelength out of phase. There we go. So what does the acceleration look like? I'm going to take it away. The acceleration would be the exact opposite of the displacement. So our acceleration graph would look like that. Sorry, my amplitude must be more or less the same. So we say, when we have simple harmonic motion, regular, repetitive to and fro motion, we say that the displacement time, the speed time, and the acceleration time graphs, they lag 1/4 wavelength behind. So velocity time will lag 1/4 wavelength behind the displacement time. And the acceleration time lags 1/4 of a wavelength behind the velocity time, which makes it a 1/2 wavelength behind the displacement time. Okay. This is there on the next page. No, that's about it. All right. On the next page, I just want to go through it with it. There they explain figure 13.4. Velocity is maximum positive when the displacement is 0, just from the little graph there. And then they say, how does the acceleration of the bob change over the cycle? And if you go and look at figure 19.5, there you will see they show that the acceleration lags 1/4 wavelength behind the velocity time graph. They say in simple harmonic motion, the displacement lags behind the velocity by 90 degrees. Why 90 degrees? It's 1/4 of a wave cycle. All right. Now, circular motion, if I had a piece of paper that was moving, you get a graph, okay? So 1/4 cycle is 90 degrees. So they say then, ek lees weer, in simple harmonic motion, the displacement lags behind the velocity by 90 degrees, and the velocity lags behind the acceleration by 90 degrees. Okay. Forced oscillations and resonance. Just very simply, there they have the picture of Barton's pendulum, and below that picture one, the second paragraph, you will find that eventually the pendulums will all oscillate at the same frequency, but they will vibrate with different amplitudes. And then which one will the amplitude increase? The one that has the same natural frequency as the forcing frequency of the weight, and we find that the amplitude will increase. This is resonance. Okay, forced oscillations. All pendulums will oscillate with almost the same frequency despite their length. The frequency is not the natural frequency of the pendulums. The oscillations were, in other words, forced. It's interesting to note that these oscillations were quite small. All right. On the next page, there, yes, we've done it. It's resonance. It's just the definition of the resonance is there. They say, we usually only notice forced vibrations when they cause resonance. All right. Resonance happens when the forced vibration happens to be the same as the natural vibrating frequency. It's like a swing. If I force it at the same frequency that it is swinging backwards and forwards, it's going to go higher up with each push. They say, yes. Then they say, resonance happens when a forced vibration happens to be the same as the natural vibrating frequency of the object. In Barton's pendulum system, one of the pendulums was the same length as the driver pendulum. This one started to oscillate much more than others because the frequency of the forced oscillation was its natural oscillating frequency. Yes, you can ask a question. Yes. Yes. You are moving. Once you are moving. If I lift you up and I let you go. If I pull you to the side and I let you go. When you get down here, you'll be on your maximum speed. All right. People, music instruments. For example, a guitar. And I'm not talking about electric instruments and all these funny things. But a normal guitar, it's got strings. And it's attached to a hollow box system. And if you pluck the string, the vibration is transferred into the box, and the box starts vibrating at the same frequency as that of the string. It's one of its natural frequencies. And that allows resonance to occur for you to hear the sound. If I spun a guitar string very tightly as it is on the guitar, and I plucked it in air, am I going to hear it? Hardly. Maybe very, very slightly. We can hear the sound from the guitar because every single string that you pluck causes a vibration of a specific frequency, and the box of the guitar is designed to have various natural frequencies that correspond with the frequency of the string. And that is why the sound is amplified, because the vibrating, the forcing frequency is the same as the natural frequency. And the amplitude increases. Yes? Yes. If you have a flute, just a normal ordinary flute, a straight flute with holes in it, what you actually do when you close and open up holes, you're changing the length of the column of air. You blow air through it. The air vibrates in the column. By closing certain holes, you change the natural frequency of the flute. And depending on the frequency with which you blow into the flute, it starts resonating. And that is the one that you will hear. Yes, yes, it's also just air moving along a column. All right, and when a resonance occurs, that is the sound that you hear. All right.
Win free airtime with One Africa TV. Share your comments on the channel. WhatsApp your feedback, name and town to 081 200 6659. One Africa TV.